from Suzhou University to share with us some of his recent research. Professor Zhu is an associate professor at the Suzhou University, and he did his bachelor's in the undergrad and also PhD at the University of Tokyo. He got his PhD in 2019, and then he worked as a postdoc in the Institute of Advanced Studies at Dublin, Ireland. And from December 2020, he started to work at Suzhou University. And his research area includes conformal field theory, supersymmetric field theories, and also string theory related mathematical physics. Yeah, let's welcome.
Well, thank you very much, and it's quite a big honor for me to give a talk here, and also I would like to share some recent very small progress from our recent research team. So I'm going to talk about, I'm going to give a quite brief introduction to this so-called Bethe gauge correspondence, which I will describe very soon. And from here, I would like to show you that actually we can use some technique in supersymmetric gauge theory or like string theory, things like that, to count the like Bethe states in some integrable models. So conceptually, it looks like this. We would like to consider about this kind of correspondence or duality, we sometimes call it. It's well, we know that in general, it's difficult to solve like a quantum many-body problems, and also it's difficult to solve quantum field theories. But in some special cases, actually, we could solve the systems in a very exact way. For example, for quantum many-body problems, we know that there's a class of theories known as the integrable models that has as many conserved charges in the system as the number of degrees of freedom in the system. So this allows us to solve the, for example, the spectrum of the model exactly via a technique called Bethe ansatz. And on the other hand, if we consider like quantum field theories with a lot number of supersymmetries, with enough number of supersymmetries, there's a very nice technique called supersymmetric localization technique, which allows us again to compute, for example, the path integral in an exact way, including the non-perturbative corrections. So these are two very different subjects, but surprisingly, people found that they are actually due to each other, or they have a kind of correspondence. So what I would like to show you is that first I would like to tell you how this kind of a correspondence holds. And then I would like to show you how the technique on one side may help to solve some difficult problem in the other side. So we have two systems that are exactly solvable, but we are using different techniques to solve these systems. So in general, like some quantities on the left-hand side is easier to be computed from, say, Bethe ansatz, but some quantities will be easier to be computed from this right-hand side from the localization. Well, this is the plan of the talk. Well, I will try to go as slow as pedagogical as possible. So if you have any question, you can stop me at any time. So we will begin with the gauge theory, or it's a special quantum field theory with gauge symmetry. And in this theory, we have, well, it's usually first labeled by a gauge group. Usually we choose a Lie group G. And it will give us the gauge field. Well, in physics, we call it like a gluon or photon in this theory. And then we also consider some like fermions in some representation of this gauge group G as a quarks in our real life. And we should consider like interactions between these quarks and the gauge fields in an invariant way under the gauge symmetry. So that is basically, roughly speaking, the idea of the gauge theory. By adding supersymmetry, we are introducing some new symmetry in the system. And roughly speaking, the supersymmetry is a kind of a rotation mixing bosons and the fermions. So it changes the bosons into fermions and the fermions back into bosons. So for example, it forces the gauge field to have a super partner called, for example, gluino, and they form a vector multiplet in the theory. And also, if we consider like a quarks in the system, it will be paired with some boson, usually called like quark, or well, it's a scalar field in the theory, and they pair into a chiral multiplet. So first of all, the supersymmetry tells us that we need to introduce more fields into the theory. And also, actually, if we increase the number of supersymmetry, of course, the interaction should be invariant under the supersymmetry. So this will strongly restrict the form of the interaction. So when the number of supersymmetry gets large, actually the Lagrangian of the system gets very rigid, and usually it can well, only be labeled, for example, by the gauge group G, and also the representation of the field of the quark we consider. So that's a rough idea, but why do we want to consider supersymmetry? It actually makes the system more complicated. We are introducing more fields into the system. We have more degrees of freedom. However, if we have a supersymmetry, we can use the technique called localization. So for example, if we schematically denote this as SUSY transformation as a delta, it converts a, for example, scalar field X into a fermionic field psi, and so on. Then we can see if we can compute the path integral, but because of the invariance of the supersymmetry, we will see that we can deform this path integral, for example, on the left-hand side, to, well, by adding this kind of exponential term, because well, it's a exact, well, it's a delta exact term. So we will see that the path integral does not depend on this deformation parameter t. So we can change any t to do the computation to calculate this path integral. However, if we choose t to be infinity, then this calculation.
Sorry, I'm not quite familiar with this kind of formalism. Are you assuming this delta w is a function of x and psi, or is it constant?
Yeah, delta w. Well, w is like a kind of Lagrangian or kind of potential. It's a function of x and psi, and well, delta w itself is again complicated. Yes. And well, the only property we need is that well, if we transform twice, because it's a kind of fermionic symmetry, it will be like a 0. So delta w is the what?
Delta w is the 13.
Well, delta w is a super symmetry transformation of w. So you see, in w we replace like x to be psi to get this delta w. Yeah, it's a SUSY. Well, you can think of it as an infinitesimal. Well, not really the. Well, it's just the transformation. Yeah.
So what the W means, that the W means some classical fixed point of W of the potential, or some other means.
Well, W is like a superpotential, as the professor was
Yes, I know,
saying.
but my question is that this represents some classical value of some potential rather than an arbitrary value.
Yeah, well, usually it's like related to like the Lagrangian in the system. Yeah, well, yeah, well, in principle, we can like, well, if it satisfies this, we can add anything like here to do the calculation, right?
Is this just a representation of the integral and representation?
No. I don't think so. Well, it's just
T to NT. So the
yeah, actually for any t, this holds like the left-hand side equals to the right-hand side, but we can also take t to be infinity. That's spirit. So well, once we take t to be infinity, we will see that the only contribution comes from like w equals 0, right? Otherwise, this exponential will be gone. So what we need to do to calculate the path integral is now simplified to the Gaussian integral around the fixed point of this delta w equals 0.
Is that psi and x and w are all real or complex?
Usually, I think it can be like complex fields. Yeah, but it doesn't really matter.
But what if w is complex? It will be what will happen if delta w is complex?
I think usually, well, like well, delta w is something very similar to like Hamiltonian or whatever. So we would like it to be like a positive definite. So yeah. Yeah, so in this way, this allows us to calculate the partition function of the supersymmetric quantum field theory in an exact way, and schematically we will have this path integral equals to some like a summation, well, some contributions at each fixed point, and we just sum over all the fixed points given by this delta w equals 0. So that's the advantage of this supersymmetry. And now we can try to apply this thing into, for example, 2D n equals 2, supersymmetric quantum field theory. That is one main example in our talk. So in this theory, actually, we can derive, well, usually we have a theory and we can consider like RG flow to flow into the IR to consider about the effective dynamics of the theory. And actually this effective twisted superpotential that controls this low energy behavior of this theory is given like this. I'm going to tell you how to derive this in a second. And here, what matters is that we have some scalar fields sigma appearing in the vector multiplet. And if we want to compute, for example, the vacuum of the theory, of course, we want to minimize this superpotential. So this will tells us we have some non-trivial, well, we can give some non-trivial VAV to the scalar field in this vector multiplet. Well, there's some technical detail that we can actually add some magnetic flux further into the system, and we will see that the vacuum equation is given by like it's kind of the saddle point of this twisted potential, and finally the vacuum equation is given by this exponential of the partial W over partial sigma.
If you know a vector field for some parameters.
Rho is a wild vector in the Lie algebra. If you know the algebra, it's like if you have the root, you will have y vector as I think it's a half sum of all the positive roots or something.
The zero in sigma, is the function of x and psi you gave in the last lecture, last page.
Sigma is like something like x.
Okay.
Yeah, here it's a schematic thing, but sigma you can think of it like x, and rho is, as I said, it's a Lie algebra thing.
What is RJ?
Where? RJ is a representation of the quarks I mentioned. So we have a bunch of quarks, and we sum over all these quarks. And W is the weight of the representation. So for each weight, we have although for quarks, we usually take a fundamental representation in our real life, but we can consider any representation. So for each weight, we are actually having one quark in the system. So we are summing over all of them.
What is sigma U1J?
Sigma U1J is U1 part. Well, sigma is actually a joint representation of the gauge group. So sigma U1 is the U1 part of the gauge group. So corresponding to that, we can have a linear combination of sigmas, like a lot of sigmas summing up together to have this field. J is a coupling. It's called a Fi parameter. We can add into this. Yeah, whenever we have a U1 gauge group, we can add this coupling.
Is the 2D theory defined only by the superpotential?
No, we have a Lagrangian. We can again do what I told you, like
or some real function also.
Real. In this case, maybe real. Yes. Well, we have some like a superpotential. We have some.
But you only need to define the superpotential.
No, this is the low energy effective description of the theory. So we have some Lagrangian description in the UV, and we are flowing to the IR. In IR, we are expecting kind of maybe a strong coupling behavior.
If you need to specify this W effective to get the theory.
Yes, in the low energy field theory, we are expecting this is the only thing we need to describe the physics.
Is this W real or
I think, well, because sigma, well, it's hard to say. Sigma, I think it's a real scalar field. So we have 2 pi I.
If W is not real, this positive real. Is this?
This W is not that W. Yeah, and also yeah, well, it's like well, because we are actually solving like 2 pi I into this. Yeah. Well, yeah, let me tell you how to derive this effective superpotential as an example. For example, we know how to do the localization computation for dn equals 1 supersymmetric series very well. And so we can put this theory on a, well, C is a complex plane, like a C times torus, this kind of background. And if we take this torus to be very small, we are getting a 2D theory. And this theory will be defined on a so-called omega background. We are actually twisting this space a little bit. Well, this is not important technical point. And then we can see that actually computing this partition function, the partition function of the theory will tell you that the partition function is split into 2 parts. One is classical and one loop perturbative contributions, and the other is non-perturbative contributions from vortices. So from localization technique, I told you, we can actually obtain this the formula for the partition function like this. So how to extract out this effective twisted potential is that we can, for example, take epsilon to be 0. That is a flat space limit of the theory, and we try to read out the leading order, the effective potential. That is the W I gave you. So for the localization technique I told you, we can get this, and by further taking some limit, this is what we usually call like a thermodynamic limit of the theory. We are getting this effective superpotential. So let's do some small computation. For example, we consider a theory like a UK theory with NF fundamental matters, fundamental quarks, and well, we can just put the roots and also the weight of the representations into the effective superpotential to write down the explicit form like this, and we can compute the vacuum equation. We already had the equation. It's very easy to do that. And we see that the equation looks like this. So it's just, we see that all equations, they are independent, right? We are getting K independent equations, and these are all like degree NF equation. So for each sigma, we are just picking like NF solutions, one of the NF solutions to give the VF of to this sigma. However, if we look more carefully into the expression I gave you here, there's a gamma function here. And well, alpha is the root of the system. So here we are actually having like a sigma I minus sigma j in the gamma function. So if sigma I equals sigma j, we see that well, the gamma function becomes divergent, right? So this will be 0. So it will killing the contribution to the partition function. So from here we see that there's actually a hidden requirement saying that sigma I cannot be equal to sigma j. So at the end, the independent number of solutions of this vacuum is actually well, NF chose K. That's how we count the number of vacuum in the system. I hope this is clear. This is a very simple example. And now we can go to some more interesting example. We consider, again, this UK gauge group, and we consider NF fundamental matters like quarks. And also we add NF anti-fundamental matters. And on top of that, we further add one matter multiplet in the adjoint representation. Actually, the adjoint representation will give you some contribution like this. We are having sigma A minus sigma B in the vacuum equation. So now it's a very highly non-trivial equation. We have a coupling of different sigmas in the equation. And what's the most interesting thing people observed is that this equation looks very, very similar to the Bethe equation. So if I turn off the mass, if I take a massless limit, this will be so-called n equals 4,4 theory. There's a higher symmetry. Well, because we have, for example, this adjoint representation combined with the vector field will form multiplet with higher supersymmetry, and also this fundamental matter together with anti-fundamental matter form a bigger multiplet.
The higher symmetry is N4,4.
Yes, but because we are adding massing to the system, it's broken.
So it's explicitly broken.
Yes.
Is the vector equation a classical equation? We want to solve the expected value of sigma A.
Yes. Yeah, that's the first step to get the well, like the position of the vacuum in the moduli space, right? And then we can, for example, consider the fluctuation around the vacuum and so on. So how we do the computation.
Sigma A is independent of space-time.
Sigma A is independent of space-time. You mean the dimension of the space-time?
Real space-time. For the
So here I'm considering a theory in two-dimensional space-time.
yes. Is uniform. I mean,
what do you by uniform? You mean all sigma A's, they are symmetric to each other? Yes, well, sigma A's are corresponding to like weights in this UK, so we have permutation relation, permutation symmetry. Okay, so the point, the most interesting point people observed in the literature is that this vacuum equation looks exactly the same as the Bethe equation in the Heisenberg spin chain. So back in 2009, Nekrasov and Chatashvili proposed that there's a Bethe gauge correspondence that the Bethe equation we will use BAE short for that is equal to the vacuum equation in the gauge theory. So now I'm going to tell you what the Heisenberg spin chain is and how to derive the Bethe equation for this theory. So this is a very old model proposed by Heisenberg back in 1928 or so. So we consider just a lattice of spins, and at each side the spin can be up or down, and they have an interaction that takes a form like xx plus yy plus vz. X, y, z are the polymatrices. And then, well, there are several interesting models. We are going to focus on this XXX model, where Jx equals to Jy equals to Jz, the coupling is all the same. Well, this is just a very naive model for the magnetism, but in 2031, Bethe proposed a way to actually guess the exact wave function for this one-dimensional Heisenberg model. He found that if you just guess that the wave function is this, by just requiring that, well, there are some parameters in this guessed form of the wave function. So if you require that these parameters satisfy this equation, which is now called the Bethe equation or Bethe equation, then the wave function will be the eigenstates of the system. So, well, that's a very well, strong intuition for him. But actually, with the effort of many people afterwards, now we have a quite systematic understanding of this solvability structure. So we start from what is called the Young-Baxter equation. We find a solution and we apply the algebraic Bethe. Then we can get the Bethe equation and solve the system. So let's review this process a little bit. We start from the solution to the Yang-Baxter equation like this. So the Yang-Baxter equation looks like this. We have several R matrices. Well, they are kind of corresponding to the scattering process of particles in one dimension. And well, if the many-body scattering process of the quasi-particles can be factorized into these two-body systems, we should have the left scattering process equal to the right. So this gives us the Yang-Baxter equation. And if we find one solution, actually, now we know how to construct a family of integrable models in a very systematic way. So we first find like a lax matrix satisfying this equation, like RLL equals to LLR. Of course, we can just use the R matrix as the lax matrix. And then we define this transfer matrix using the lax matrix. So in our case, I'm going to use just the R matrix. So we multiply all these R matrices together. So like R01 is R matrix acting on the auxiliary space 0 and also one real physical space 1 and so on. We multiply these R matrices together and we take the trace only on the auxiliary space 0. And then we will get a very, very big matrix called the transfer matrix. However, if we do the calculation a little bit, it's very easy to show that actually this transfer matrix, they commute with each other at a different spectrum parameter. Well, we have one spectrum parameter in the R matrix, so we can consider this transfer matrix at a different place, and it's very easy to show that they commute with each other. However, this suggests that if we do the expansion over U, for example, for this transfer matrix, we are getting a lot of coefficients, expansion coefficients at the matrices, but these matrices, they commute with each other, right? So we have this very big all commuting family operators. So if we identify one of the H, the expansion coefficient at the Hamiltonian of the system, then we are getting a bunch of conserved charges in the system. Well, in principle, it's like we can have an infinite number of conserved charges in the system, but of course the degrees of the system is finite. So in general, we are only getting as many conserved charges as the number of degrees of freedom in the system. So this guarantees the solvability or the integrability of the system. So let's repeat this process with an example. This example we want to consider is the XXX spin chain. The R matrix is known to be given by this 4x4 matrix. But it's also possible to rewrite it into a 2x2 matrix with each element as a 2x2 matrix. So we can use a Pauli matrix to rewrite this. So one can, for example, compute the Hamiltonian by first construct this transfer matrix by multiplying these R matrices together and then do the expansion. We will see that this 2 here, I think it's it means it's a 2 by how to say 4x4. Wow, yeah. Well, it's related to SU2, for example. If I use SU3, it will be a 9 by 9 matrix. Yeah, so if we compute the Hamiltonian, we'll see that exactly it corresponds to the XXX Heisenberg spin chain Bethe solved. So this explains why Bethe could solve the, well, could guess the exact form of the wave function. And of course, so this is just the spin 1/2 case. At each site, we put the spin 1/2 matrix, but we can, like here, we have some Pauli matrices. We can take different representations of the Pauli matrices, right? It does not have to be a 2x2 matrix. We can replace it by like a 3x3 matrix for spin 1 and a 4x4 matrix for spin 3/2 and so on. So for example, although it's quite technical to compute the Hamiltonian, for spin 1 case, the Hamiltonian looks like this. So it's a slight modification of the Heisenberg spin chain. And then we can try to solve the system by first we decompose this product of R matrices into A, B, C, and D. And then we can see, because, well, this A, B, C, D are just very big matrices, but we are organizing them on this auxiliary space, this zero space. And so the transfer matrix will be given by taking the trace of that operator. So it will be just given by A plus D. And then the ansatz we wish to put, which is actually the same ansatz for Bethe proposed, is that we use we first start from some ground state, and then we act this B. B looks like a raising operator in the system. So we act the raising operator in the system to generalize the general state. And by requiring that this spectral parameter UK to be some special value, we wish to get the eigenstates for the system. And then it's very easy to compute this action of the transfer matrix acting on this ansatz eigenstates. We can see that, well, because we can compute the algebraic commutation relation between A, B, C, and D, we will see that it actually looks like this, well, with some unwanted off-diagonal term. And then what we need is that, well, if this is the eigenstate, then we wish to just kill an unwanted term, and this will be a diagonal action. So to kill the unwanted term, actually it's very simple, but there's a very shortcut way to discuss this. T, we can see that it's a polynomial of U. So we wish to require that the eigenvalue of this T is also a polynomial of U. Then what we need, well, because this one does not look like a polynomial, we have a lot of residues. So we need to require that we have a lot of poles. We need to require that these residues are all zero. So this will give us this Bethe equation. That's what we had before. And so in this way, we could see that this Bethe equation looks very similar to what we had before in the supersymmetric vacuum. Of course, there's also, so in this case, actually, we are only taking the trace of the products of R matrices. So this corresponds to the periodic boundary condition of the system. Actually, one can also consider some more general boundary condition. For example, one boundary condition that could be very interesting in the later half of our talk is that when we go around this spin chain, we add a twist into the chain. So this is called the twist boundary condition. So this raising and the lowering operator is twisted a little bit. Well, this can be realized by just adding some diagonal matrix into the construction of the transfer matrix. And this will actually give us some like a theta here, and it can produce what we need for the vacuum equation in the supersymmetric gauge theory. Okay, so I hope this is clear. So we can now give the dictionary between the supersymmetric gauge theory and the integrable model. For example, if we have like NF number of quarks, it actually corresponds to the number of sides in the spin chain, like the number of spins in the spin chain. And also the rank of the gauge group in the gauge theory corresponding to the number of magnons in the theory. Magnons is like the excitation of the spin chain, like by flipping like up spin to down spin, we are generating a magnon. And also the adjoint mass in the system corresponding to the crossing parameter in the R matrix, and also the Fi parameter corresponding to the twisted angle in the spin chain. So this is the dictionary. So at this moment, we are only establishing one equation is equivalent to the other equation, but that could be a coincidence, right? But actually it's not. Actually, we can compute a lot of things, for example, in this supersymmetric gauge theories, and see that they really match with the sure.
Just terminology, so in the rank of the gauge group, what does it mean? These are unitary matrices, they are all full, right?
No, I mean like for UK, we call the rank is like K+1.
Okay. Oh, you mean the
it's K, okay.
you mean the order of the carton?
Yes. Yeah, because it corresponds to the number of sigmas in the system, and so that will correspond to this M.
So question, is this adjoint mass limited where the mass is equal to 0 is the highest sigma?
No, we also need to take the mass of like the quarks to be 0 to get that.
So
yeah, and as I said, there are actually a lot of other physical quantities we can compute, and they also match. And today I would like to talk about this one. This is, I think it's quite interesting. Actually, we will see that the computation of the Witten index, which is a very localization way to count the number of vacua in the supersymmetric gauge theory. They can give the correct number of physical states in the integrable spin chain. So there is one very big problem of the Bethe-Anders approach.
Easier to compute.
So in our case, first, this one is quite easy to compute. This one we know the like the required answer from the representation theory. Of course, we know the dimension of the Hilbert space, right? However, if you really want to count the number of physical states in the Bethe-Anders equation, it's very difficult. So,
but you still know the number.
in some cases, yes, but in general, it's yeah, I will talk about it. It's a
general, this Witten index is still easier to compute.
yes. So yeah, as I would like to say, the big problem of the Bethe-Anders is that because it's ansatz, we don't know if it really works. Of course, if we have some solution, we know that it should very likely be giving an eigenstate for the system. However, it's really not easy to show that the number of solutions to the Bethe-Anders equation is equal to the dimension of the Hilbert space. And actually, it's not. It's very easy to see. For example, we have many unphysical solutions in the Bethe-Anders equation. For example, if we take all the spins at each side to be 1/2, this is the Bethe-Anders equation, and you will see there's a very trivial solution. Like I take Vj to be IN2, then this will be 0, right? And then I can take another Vj, say Vj plus 1 to minus 1, 1/2 I. Then we can see that this one is Vj minus Vj plus 1 minus I is 0. So this is if we multiply this equation to the this denominator to the right, we will see this will be 0 equals 0. This is always satisfied. So when we try to solve this Bethe equation, we will always find this kind of solution. However, if we really consider about this solution, we will see that the energy of this solution usually is divergent. So it's absolutely not a physical solution. So of course, then we can think, okay, then we just remove all these singular solutions. It will be done. However, it's not that simple. Of course, generically, singular solutions are unphysical, but they can be physical. That's a problem. So especially when we take theta goes to 0, that's a periodic chain we usually most interested in. And we will see that, of course, taking something to 0, we need to be careful. We need to do some regularization. So if we take this theta to 0 and we take some small number epsilon proportional to this theta, and it's going to like this I over 2 and minus I over 2 like this way, in this very specific way, we will see that these solutions can be physical. Well, the energy can be can be convergent, can be finite. So from this, we can further derive some physical conditions for these the remaining roots. It's quite complicated. It looks like this. And for example, if we have 3 magnons, one will find a physical solution with like U3 equals to 0. So although it's singular, it's still physical. So now we need to first remove some singular solutions, and from these singular solutions, we need to try to find some physical solutions. So that's a problem. And so this is a simple case with the spin equal to 1/2. Actually, when the spin gets larger, and also this is actually spin chain with SU2 symmetry. If we consider a spin chain with a larger like SUN symmetry, the situation will be more and more complicated. We can have like a so-called physical repeated solution with the 2 beta roots equal to each other. That usually doesn't happen, but they can again be physical in some higher rank or higher spin cases. And we can have like a physical singular repeated solution and so on. It's we can have a lot of paths to have special solutions. So it's really not easy to prove that the Bethe is complete for this to do the computation. There's like in SU2 case, the simplest case, and with spin 1/2, I think we have a proof like from the mathematical side. But we don't have any good insight beyond, I think.
I have a question.
Mm-hmm.
So what is the physical meaning of M?
Physical meaning of M? M is the number of magnons. I'm sorry, like I said, it's roughly speaking, it's a number of flipped spins in the system.
Because you use the little.
Oh yeah, I used the little m. Yeah. Yeah, it's the same. Okay, so we take a different approach. Let's just count the number of vacua in the supersymmetric gauge theory. So this can be done by computing the so-called Witten index. So this is the definition of the Witten index. So if we have a Hamiltonian H, we consider like the trace of this exponential minus beta H, that's the usual thermal partition function, but we add this -1 to the fermionic number F into the partition function. And then we will see that actually this Bethe index does not depend on beta, because if we have a, say, bosonic state with energy EI, then we can act this supersymmetry, well, supercharge operator Q onto the system to get a fermionic state Q times this EI, and they actually have the same energy. It's very straightforward to compute that they have the same energy because Q commutes with H, right? It's a symmetry of our system. So actually in the Bethe index, because they have different number of fermions, they cancel with each other. So at the end, we will see that the only non-trivial contribution comes from the ground states with like that. They killed by the supercharged, and they have the zero energy. So actually it's exactly the same as just writing like this. So again, we see something very similar as we discussed in the localization context. We have a deformation parameter beta, but it does not depend on beta. So we can take, for example, beta to infinity, right? So at the end, it tells us that Bethe index counts the number of vacuum in the supersymmetrical theory. And again, we can compute this Bethe index by doing some localization calculation. I'm not going to the details, but we can consider some refined version of the Bethe index first. It's called the elliptic genus in 2D theory. We consider putting this 2D theory on a torus, and then we compute its partition kind of partition function. And well, the formula looks like this. It's not so important, but we have a lot of elliptic functions. So the most important thing is that all the pores, well, we can take some limit. We can take, for example, this Z going to 0 limit, or this Y going to 1 limit to actually, because if we take Y to be 1, this will be just the Bethe index. Bethe index, and we will see that the Bethe index is just counting the number of pores in this formula. So we only need to know the number of pores. It will become very simple. And well, then it's not hard to analyze the pore structure, and we see that the types of pores is given like this, like C and chi are some fixed number, and N is just some integer. We can have some integer lambda. Well, this is generated actually from this. We can add 1 minus lambda into UI to get another pore from the previous pore. So we can actually draw a picture. This pore structure can be phrased in a very simple way. It looks like a piling boxes. We have kind of lattice, and we put this box from the bottom to the top, and we just piling these boxes in this lattice. And well, it's not easy, not difficult to see that this really looks like taking some taking some weight. Well, like the largest number of the boxes is like 2s. Well, we can also have empty boxes. We can have 0. So the pattern, we have 2s plus 1 patterns, and this corresponds to the 2s plus 1 representation of the SU2 group. So this can be interpreted as each configuration corresponds to a different weight in this tensor representation. Looks like this. So and what this is actually the degrees of freedom we put at each side of the spin chain, right? So This way we can really see that the number of vacua in the supersymmetric gauge series, they really satisfy the desired, how to say, the completeness of the Bethe equation, or well, they can reproduce the dimension of the Hilbert space very well. And it's also very easy to generalize this to higher rank cases with UN gauge with the UN global symmetry of the spin chain, and we see that well, like we have a 3D picture in this case, and at each row we are having a Young diagram, and to get the weight for this configuration, we just count the number of boxes in each layer, and well, of course, they satisfy this kind of constraint. And if you are a little familiar with these, the representation of the algebras, you will see that this has a one-to-one correspondence between each pole and also each state in the highest weight representation of SUN plus 1 gauge theory. So, for example, in the textbook, you can find something called the semi-standard tableau or Gelfand-Tetlin basis. You can really see that these numbers, because diagonal with some numbers, and these numbers are corresponding to the height of these boxes in our figure, and there's really one-to-one correspondence between one figure and the one state in the representation theory. So this tells us that we are actually again reproducing the desired dimension of the Hilbert space in our cases. But one thing to be noticed is that we could only do the computation at non-zero twisted angle theta. So at a generic point of theta, actually the non-abelian symmetry of this SUN is broken to a lot of U1s. So at that point, we are getting the correct number of solutions. What we want to know is that, well, because something special actually happens when the non-abelian symmetry is restored. So what happens when the non-abelian symmetry is restored or partially restored? Actually, we can have a look at the example. We could just solve the Bethe equation to find all the solutions. For example, if this theta is not 0, I'm taking this exponential I theta to be 1.01. It's not 0. Well, it's not 1. So there are 6 solutions in this L equals 4, M equals 2 chain. And well, I've written down all the solutions. But one thing to notice is that some Bethe roots are really big, like 100, around 100, although I'm taking it's being 1.01. If I take it, take the exponential I theta to be 1.001, this will be like 1,000 or so. So if we are really taking the limit that theta goes to 0, some of the Bethe roots actually becomes very large. It will go to infinite. Well, that's our expectation. At the end.
Become a fold and bar or distinct state.
Yes, they are distinct. Well, they actually have a meaning. Yeah, that's what I wanted to say now. Actually, well, these U, they will be divergent in this periodic limit, periodic chain limit. So we can really see that this raising operator, when u goes to infinity, they correspond to this spin raising operator. So they are changing spins. So if we act like of the highest weight state by some this rating operators, we are getting some descendant states, right? So like this 2,1 tilde and this 2,1 bar are descendant states of this 2,1. So they form one highest weight representation. So that's a point. We have all the states in the twisted cases, but when we go to the untwisted cases, with theta goes to 0, we are expecting the non-abelian symmetry to be restored, and all these states, they are trying to form the highest weight state. However, of course, if you solve the Bethe equation, you're only seeking the finite solution, so you won't see the descendant states. So to count the number of states, you need to just start from the states of the with the same U1 charge in the symmetry broken case, and remove some of the descendants. Then you get the number of highest weight states. That's the spirit. So in this way, for example, well, that is a known formula for SU2 case that can really reproduce the completeness of the Bethe. So how to understand that is that so for in a twisted spin chain with the same U1 charge, actually we are having this much space, like we are having the state that's going to be the highest weight state in the periodic case. We are also having a lot of periodic descendant states, but each descendant state actually corresponds to some, like I can remove one S, they correspond to the number of states with like one less U1 charge or one less Magnum number. So that gives that formula. We just subtract the number of solutions with the m-1 magnums from the number of the solutions with magnum number m, then we are getting the number of highest weight states in the SU2 case. So we are proposing a general formula that works in the SUN or even like all the algebraic cases that starting from the number of states with a given U1 charge, we can just do some computation to get the number of the highest weight states. So that's, well, I don't want to really give you the details, but this tells you how to remove these descendant states in this calculation. And well, this theorem, actually, if you just consider a simply case with two sides, a proof can be found in that CFT book. It's very simple, but well, we are considering like the tensor of arbitrary number of sites. Well, how much time do I have left?
I think you really good.
Okay, okay. Now I'm wrapping up. So I don't want to go to the details. So let me just give you one more point is that this formula actually does not only work for like A-type Lie group, we also expect it to work for others. And well, I don't want, and this tells us actually, if we start from the, just by looking at the vacuum of the supersymmetric gauge theory, we should be able to find all the physical solutions in the periodic Bethe equation. And yeah, one interesting thing I would like to stress at the end is that it also works for the super the algebra case. And in this case, we can consider some very strange model, like it's called the TJ model. We have like electron, we have holes in the theory, we can have some hopping and also spin interaction among these electrons. And this theory actually has a SL1/2 Lie superalgebraic bigger symmetry. And in using our way, we can also show that the number of states counted by the Witten index, for example, given by this, they really give the complete, well, it's still a conjecture though, but in some simple cases, we can really show that they give the full dimension of the Hilbert space. So I'm not going to give you too much details. This could help us to consider the calculation, how to really modify. Well, this guides us to find the on the physical solutions in the spin chain gauge in the spin chains. Okay, so let me summarize. I think I reviewed how the Bethe gauge correspondence works, and I showed you it's not just a coincidence of two equations. It can be quite helpful in the study of, for example, spin chains by just computing the vacuum of the super symmetric gauge theory. So in this process, we proved a kind of a new mathematical theorem that helps us to understand the completeness of the Bethe index. And well, there can be a lot of interesting things to be done in the future. We wish that, well, because the integrability community actually has a longer symmetry and a lot of more sophisticated techniques, maybe in the future we can borrow some techniques from there to study gauge theory. That could be more interesting. But yeah, we are still lacking like dictionaries between these two correspondence. So if you are interested, we really need more people to join the field. Yeah, that's all I wanted to say. Thank you very much for attention.
Any questions?
Can you go back to the slide with the correspondence between symmetric Bethe
Like here? This one? This one?
So for the limits of mass going to 0, what does this correspond to? The symmetric theory, is this also relation?
So like we want to assuming this, so this will be gone, and this will also be gone, right? Well, like naively, everything will be gone. It's a little problematic, I think. Well, if you want to really give a valid discussion, actually at the level of localization, usually it breaks down. So you cannot just directly take that limit. Yeah, but of course that would be a very interesting case. Usually in this kind of degenerate case, we have like things like a double pole, continuous pole, things like that. People usually don't want to face that, but yeah. Yeah, but of course, if we can really deal with that, it would be very interesting.
Yeah, question.
Oh, sorry, this is not your question. Can you generalize to the UQSU2?
UQSL2, you mean XXZ spin chain?
Yes, exactly.
Yes, yes, of course. Of course.
Because I know there's a, I don't know if I remember correctly, there's a, like, you can use the R-metric formalism, the R isomorphic to the generator of the UQSU2. Yeah, that's just my question. Can you some the same technique can generate to
Yeah, I think so.
and
And
counting the Wheaton index and things.
yes, yeah, like conceptually it's almost parallel, but
Right.
technically maybe a little different. Especially in the UQSL2 case, one would have this root of unity problem, like at
But if we only consider Q generic phase,
Q generic, I would expect it's almost the same.
almost the same.
Yeah, yeah.
I think RDF they show there's the same thing.
Yeah, yeah, yeah. But at the root of unity, there will be a lot of interesting things happening. I expect.
Let me try to ask some wild questions. Actually, I don't know much about the data assets or the future. Anyway, can this be generalized to higher dimensions? I think it's you have a correspondence between 1 + 1 dimensional quantum field theory.
Yeah, like XXZ can talk about it's expected to correspond to 3D gauge theory.
Oh, I see.
And the XYZ is expected to correspond to 4D gauge theory and so on. So,
So the other side, the field theory can be higher.
yes, yes. Although, like, I'm not sure, like in the integrability side, we can like have a tetrahedron equation. It's a very technical thing to go to 2D, but yeah, it's too technical.
Does this hold if we add some perturbations to the break the supersymmetry?
Not sure. Not sure. Like,
But it means a wild question because we can actually, even if there's no integrability, we can still solve the one-dimensional speed chain quite reliably.
yes, exactly.
Correspondence to field theory.
Yeah, naively speaking, I would expect if we just add some perturbation, it should work. But yeah, so far we don't have a very reliable dictionary to do the calculation on both sides, so I'm not sure. Also, for example, there's something we try to consider a little bit, something called TT bar deformation. It's a deformation that preserves the integrability of the spin chain, but the spin chain will be long range interacting. But yeah, the gauge theory side will be very complicated. So yeah, I'm not sure how to really deal with it in a very rigorous way. Yeah.
Ideally, if we can prove if there's a reverse correspondence, then we can solve the spin chain and so say something about the field theory that we couldn't solve.
Yeah, that's very what I really want to do. Yeah.
Maybe a related question. So far, apart from providing a dictionary between the duality between gauge theory, supersymmetric gauge theory and integral models in Laplace one dimensions, can you use those formalism to predict new type of integrable models?
Maybe. Yeah, actually, there are a lot of vacuum equation we can get in this supersymmetric gauge theory.
A new type of integrable.
We would expect so, but it's difficult because you need to find really a corresponding R matrix to prove that statement. Yeah, but we do have a lot of more like vacuum equations from the gauge theory, but we cannot seek the how to say, the corresponding integrable models. So they might be also integrable.
No questions, let's thank the speaker, Professor.
Thank you so much.